Now it's time to investigate how images are formed from simple thin lenses. Okay, so this is the topic of ray tracing, and how do we determine where the image is going to be and what the magnification is going to be. Okay, so our main questions are: one, where will the image be? And two, what is the magnification? Okay. Now, there are really four scenarios that we're going to investigate. Okay. But for the moment, our assumption uh, for this lecture is that the curvature on both sides of the lens is equal. Okay, so the radius of curvature for the near side of the lens is going to be equal to the curvature at the far side of the lens. Now, suppose I have an object, okay, and we have what we call a converging lens. This is also a convex lens. Okay, so when the bowl shape is outward, this is a converging lens. And as we'll see, what this means is that it tends to make the light rays converge. Now, that's not always going to be the case, as we will see, but for an object located at optical infinity, it will converge. Okay, so that's why this is called a converging lens. Now, we have a few points of interest along the along the way that the rays can be generated. Okay, the first thing is to note that we have an optical axis here, and your optical axis basically cuts your lens in half. Okay, now as we saw in the previous couple of lectures, each lens is going to have a focal length. So we label the focal length as f, and the actual point, and by the way, the focal length is measured from the center of the lens out to where the light would get focused from optical infinity on the other side. And capital F is the actual focal point. So the focal length is the distance from the center of the lens to the focal point, and then the focal point is the physical point in space associated with where the light rays from an object at infinity would converge. But if this is a symmetric lens, then we could just as easily put our object on the left, or on the right side rather, and let the rays go to the left, and they would also then have a symmetric path in that it would go through the focal length on the left side of the diagram. Okay, so for a symmetric lens, you have these two focal points, and they are going to be equidistant from the center of the lens. Okay, so our scenario that we're going to start with is we're going to label this distance from our object to the lens, and by the way, everything is going to be measured from the central axis of the lens. Okay, so we're going to label this D0, and that is going to represent our object length. So D0 is object distance from lens, and DI is going to be the image distance, and we will then also compute the magnification M. Okay. Now, so what happens here? Okay. So your object is either typically going to be giving off, if it's its own light, if it's something like a candle or a flashlight or a light bulb, it'll be giving off its own light. If it's not, then it'll be reflecting its own light. And typically it will be giving off light in all directions, right? So it'll be giving off light in all directions everywhere. And because it's giving off light in all directions, there are a few specific rays that will interact with the lens that will allow us to determine where my image distance is going to be, okay, at least graphically, right? Now remember, this is all conditional on this equation. Okay? This is all conditional on this equation. So if you're given the object distance and the focal length, then you can automatically compute where the image is going to be, but that doesn't necessarily enlighten you visually, right? And that's why we like to use these ray diagrams, because they're very, very useful in actually seeing what's going to be happening with the light rays. So we use 3 special light rays. And the first is that an incident ray is parallel to the optical axis. Okay, and actually, let me put this on a different slide because we're going to run out of room here real quick. Okay, so let's put it here. So actually, let's just draw a table. That'll be easiest. And so I'm going to label these incident and refracted. So if your incident beam is parallel to optical axis, this is special ray number 1. When it's refracted, it will be refracted through the opposing focal point. Now I need to stress, this is for specifically converging lenses. Okay. A second one is if the incident beam is goes through the near focal point, then it emerges parallel to the optical axis. Okay. And then number 3, okay, this point right here where the central axis of the lens intersects the optical axis, we call this the center. Oops. We shouldn't say unrefracted. We'll just say doesn't change direction. Okay, so these are our 3 special rays for our converging lenses, and let's see how these work. Okay, so let's look at these 3 special rays, and let's look initially at a ray that is whoops, didn't want to do that. Oh, hang on. There we go. Okay. See if we can get this as parallel as possible. Right about there is pretty good. Okay. And we'll make this red or orange. Okay. So here's my incident beam that is initially parallel with the optical axis. And according to our chart here, it'll go through the opposing focal point. Okay. So the emerged beam will come here through this focal point. Okay? And the beam still goes on forever, all right? Our second special ray goes through the near focal point, and then it will emerge parallel. So if we have a beam that goes through the near focal point like this, and oh, I don't know, maybe green, it will emerge parallel to the optical axis. Whoop. I wanted to stretch this out. And let's go again with green. Okay. And actually, I need to make this line longer. Oh no, they're not going to intersect. Oh no. We'll fudge just a little bit and we'll have it intersect there. And technically it should go through the whole thing, or it should go through the center of the focal point. Okay. I just didn't give enough room. Our third beam goes through the center. And again, these are not the only 3 rays that the beam will have. Okay, and you'll notice that even this one's going to be a little short as well. I'm fudging on this one just a tad. But you'll notice that they all converge at this point. And this is why we call them this is a converging lens. Okay? So all of the rays converge at this point, and if we extend the optical axis out, then we can see that our image, where's my shape? Here we go. My image is going to be right here. Now I'm thinning it out a little bit for the sake of this diagram. But so there's some things to note here. Okay. First things first, in this case, well, okay, so very first things first, this distance now is di. Okay, so the first thing to note is that the image is inverted or upside down. And if you've ever held like a magnifying glass out at arm's length, you've actually seen this. You've observed this effect. And number two, we specify the height of the object to be h naught or h0, ho for height of object. And then we denote the height of the image to be hi. Right? Now, once again, you can use this formula assuming you know d0 and f. You'd be able to use this formula to find where the image is. And your magnification actually has two formulas. Okay? So m is equal to the negative of hi to h0, or it is equal to the negative of di over d0. Okay? Now, so there's a couple of things. There's more to this list. Okay, so number one, the image is inverted. Number two, the image is real. What do we mean by a real image? So a real image is when the light rays converge. So my light rays have physically converged at this point. And that is what we mean by a real image. And so your magnification, okay, is going to be well, let's assign some conventions here. Okay, so for converging lenses, okay, di is positive if on opposite side of lens from the object. Okay. Make that a little bit better. Okay. So di is positive if it's on the opposite side of the lens from d naught. It would be considered negative if on the same side. Okay, so these two rules are going to govern what sign you put in for um, your magnification, di and d0 with your magnification. Now, typically d0 is always going to be positive, but di can be positive or negative. And so if your image is on the same side of the lens as your object, then it'll typically be negative. And if a third point here going along with these two rules is that if m is positive, then your image is upright. If m is negative, image is inverted. Okay? Now, the situation that we have for this particular ray diagram, this entire situation is the ray diagram for d0 being larger than your focal length. Okay? And points 1 and 2 over here are going to be general under that condition. Okay? When your object is at the focal point, then you can, so if I move this object, if I were to scoot this object inward so that it then were at the focal point, what would happen? Okay. In that case, then d naught would equal f, and we would have 1 over f equals 1 over f plus 1 over di. And this would be 0 equals 1 over di, which implies that di would be at infinity. Okay? So when you push your object to the focal point, your image then disappears. It gets really, really blurry. Okay? And if you've ever held a magnifying glass out at arm's length and then moved it much closer to your eye, then you do see a point at which everything becomes very, very blurry. And that's exactly what's happening, right? So when you're, for converging lenses, when your object is larger, your object distance is larger than your focal length, then your image will be inverted and it will be real. And because it's inverted, that means our magnification will be negative. Okay? So, this is how you find the ray diagram for this particular situation. But what about the situation where my object is less than my focal point, or my focal length rather? So, what if we put an object right here? And actually, let's move it inward just a shade. Okay? So what happens here? Well, we look at the same rays, okay? So if I have a ray that's parallel to the optical axis, it will then be refracted through the focal point on the other side. And let's just make this a shade longer. There we go. And let's make you orange as before. And so we do the same thing. Okay. And again, let's actually look at the third ray now. Let's draw one through the center. And hopefully you can see what's happening. Okay, so my rays on the other side of the lens are diverging. They're getting wider from each other, right? And by the way, I can't have a ray from the object go through the focal point on the near side and then also be refracted through the lens, because if I have a ray starting here, why? Oh, didn't want to do that. There we go. So if I have a ray, let's actually start it at the focal point. If I have a ray coming down from my object going through the focal point, it's not even going to hit the lens. So we can't use that ray. But there is a ray related to that we can use. And that is if a ray in the same direction as the focal point, as coming from the focal point, I really should say, right? If there's a ray that is emitted from our object that is in line with this one as having come through the near focal point and then refracted through, this ray then gets refracted parallel to the optical axis. I didn't make my diagrams big enough. I thought I did, but I didn't. And this one really drives home the point that these rays are diverging, right? So what to do? Okay. Well, we extend, and let's actually line those up a little bit better. And we need to bring you down a shade. Okay. So if we extend these rays backward, where these rays that on the right hand side of your lens, if there were no lens, this is the point where your rays would be originating from. That's the point. Okay. And my artwork is not going to be fantastic, but we'll roll with it. Because ideally, these would converge at the exact same spot. And they're not exactly going to. But what to do in that case, if I could draw a straight line for the life of me. Okay. They should converge at a specific spot. Okay. But my artwork is not the best. Actually, I think I can do the orange a little bit better. I think I curved the orange up a little bit. And that's a little bit better. Yeah. Okay. So they converge at this point right here, right? And this is where our image now is. Okay. So This is now d0. This is now di. But because di is on the same side of the lens as d0, this is now negative. Okay? This is now negative. And our image is upright. And this is a virtual image, meaning that the light rays physically didn't converge, but they look like they were originating from that source. Okay? So, your virtual image occurs when your light rays do not physically converge, but they look like they came from a convergent source. Okay? And so, with this in mind, our magnification would be positive. And there's another point about magnification that I didn't make on the last slide, and that is if m is less than 1, then the height of your image is less than the height of your object, so your image looks smaller. If your magnification is greater than 1, then the height of your image is greater than the height of your object, and you've enlarged your object. So in this case, for the object distance being less than the focal length, our magnification will be greater than 1. All right? And it's plus, meaning that our image is upright. Okay. What about diverging lenses or concave lenses? Okay, so we'll try not to make our objects quite so large this time. And we start with the situation where our object is beyond the focal point. Whoa. How did you know? And let's bring you down a shade. Okay? And maybe even bring you a shade closer. So this actually, let's bring you out here. It'll be a little bit easier. So now D0, this is F, this is C, this is lowercase f, okay, and this is D0. Oop. Let's make this a little bit longer. Okay, so with these rays, when special ray 1 our first ray is parallel to the optical axis. Since this is what is called the diverging lens, okay, what happens is that this beam gets refracted this way, okay, but it actually gets refracted in such a way that it looks like it came through the near focal point. Why am I not drawing? Oh, I'm still in format shape. Here we go. I need to draw a better line there. Okay, so our refracted beam will follow that dashed line outward like this. Okay, and our beam that goes through the center will be unrefracted. I shouldn't say unrefracted, undeflected. I said that earlier too, but it's actually just undeflected. It is absolutely refracted at the surface, but the refraction results in no general change of the direction of the beam. Okay? Now, one thing I didn't mention in the last slide is really you only need two of these beams. Okay? You only need two of these beams. And where they cross, your image will be. Okay? So my image would be right here. Okay? But for completeness sake, we draw the third one. And the third one says, if I draw a beam, or not draw a beam, but any beam that starts at this tip and goes through the focal point on the other side, actually then emerges parallel to the optical axis. So let's make this one a striped line, indicating this is not the actual beam, but the path the beam would take if the lens weren't there, like our other dashed beams. But the actual refracted beam emerges parallel to the optical axis. And this one is green. Okay. And as you can see, these three physical beams here we go, are diverging again, all right? But if I extend the last ray that we drew, if I extend this parallel beam backward, you'll notice it intersects right here with our image. Okay, so any two of your rays will work because all three will converge at the same place. And so number one, for our special rays, number one is the beam. Oh, by the way, this is once again for when DO is greater than F, right? Initially parallel to the optical axis, emerges such that it's in line with the near focal point. Number two, let's do the green one, right? So beam that would go through far focal point emerges parallel. And number three, a beam that goes through the center is undeflected. Okay? And the general conclusions are one, that your image is virtual. Since it does not exist from actually convergent light beams, because the actual light beams are diverging on the other side. Number two, the image is upright. And number three, the magnification is less than 1 because my image height is smaller than my object height. So these are the general conclusions for when your object distance is larger than your focal length for a diverging lens. What about the last case? When our object distance is less than our focal length. So here we're going to put our object. Right here. Okay. And our three special beams are going to be very similar, okay? So if I were to draw a beam that is parallel to the optical axis, this beam emerges as if it had come through the near focal point. So let's actually draw this, and maybe this is the way to go with these things. There we go. And change color. And then if I come back here to draw with the white, oh man, I lost my cursor. Oh, there we go. So once again, the dashed beam represents the virtual beam. Okay. And so our merged beam looks like it came from the near focal point. The beam going through the center again remains undeflected, so let's draw that one next. Oop. And automatically we can tell where the image is going to be. The image is going to be right here. And so our image distance is right here, right? And then the third beam drawing through the opposite focal point so once again, right here, it will look as if this was coming from a ray that was initially parallel to the optical axis. So, no, I'm sorry, it will emerge parallel to the optical axis. It won't look like it is, it will emerge parallel to the optical axis. And so, yeah, that's going to be good enough. Once again, this is the this actually is not the virtual beam. This is just the path that the beam originally going through the lens would take if the lens weren't there, if it was pointed at the opposite focal point. This is the actual emerged beam, but it looks as if it were coming from right here. And that one's pretty good. That one, all my light rays converge. My virtual light rays converge. Okay, so that's pretty good. So the general conclusions to be drawn when your object distance is less than your focal length for a diverging lens is that your image is upright. 2, it is virtual. And 3, the magnification is less than 1. Okay? So, these are the 4 basic ray diagrams for symmetric thin lenses. Okay? And the symmetry part comes from the curvatures on both sides is the same. All right? So let's close out with an example. Let's actually throw numbers into this example right here that we did. Okay, so for the converging lens, let's let D0 be 30 centimeters. And if D0 is 30 centimeters, then this might be like, I don't know, 18 centimeters. So our focal length is 18 centimeters. And let's just make sure our math checks out with our conclusions, right? That the image is inverted, the image is real. and what our magnification is. Okay. So if this is all we know, right? We know that our focal length is 18, and we know that our object distance is 30. Okay. So A, we want to calculate where the image is. B, we want to calculate the magnification. Okay. So for part A, we have 1 over f is equal to 1 over dO plus 1 over di. Now there's one convention that I really should mention, okay? And that is f is positive for converging lenses and it's negative for diverging. Okay? Positive for converging and negative for diverging. So here our focal length is going to be positive since this is a converging lens. So 1 over di is going to equal 1 over dO minus 1 over f. Right? And no, that's not correct. It's 1 over f minus 1 over di, or d naught rather. Okay? And I need to get common denominators. So there's my common denominators, and this is still 1 over di. And then I can take the reciprocal of both sides. Whoops. This is dO times f, now that I'm taking the reciprocal, over dO minus f. So this is going to be 30 times 18 divided by 30 minus 18. And notice that my units are going to be centimeters. And so this is 30 times 18. And let's see if we can be clever here, divided by 12. So 12 divided by 6 is 2. And 18 divided by 6 is 3. 30 divided by 2 is 15. 15 times 3 is 45. And that checks out, right? So our object in this case is going to be further than the focal point. That's not always necessarily going to be true in this case. You just need to let the math play out and let the math. But it is consistent with our picture here in that we kind of fudged to put everything in the picture, but this could have extended a little bit further. So it's really easy to believe that if this object distance was 30, then that this image distance might be more than that. And so this is consistent with that kind of intuition. And then and by the way, so this is positive, so that means it's on the opposite side of the converging lens. And so our magnification then is going to be equal to negative 45 over 30, or negative 1.5. The negative sign means it's inverted. And since 1.5 is larger than 1, this means it's magnified or enlarged. Let's use enlarged because it's magnified either way, but enlarged means bigger than your image is bigger than your object. Okay? Um, and because our rays are converging at this specific spot, we can claim that our image is real. Okay? So there's a lot of information that you can glean just by knowing what your image or your object distance and your focal length are. You can calculate everything else you need about your system from just those two inputs. Okay? And you could also then explore things with the heights of the objects in the images if you knew what the height was. We don't do that here, but you could via the equation for the magnification, where magnification is negative mi over mo, or di over do rather. Okay. So I hope that this gives you an idea of how your ray diagrams work for our four general cases, and whether the object is real and upright or not. That will generally be true in all four cases. The result that we got will generally be true for all of those four cases. Okay. Um, and I think that that's it for ray diagrams with thin lenses. And we will see you in the next lecture.